Hello, my name is Santiago Correa, a fourth-year PhD student at UMass Amherst, working under the supervision of Professor Jay Taneja. Today, I want to talk about our project called GridMapper, mapping electricity infrastructure in developing countries. Accurate map of electricity grid rarely exists in many developing regions. Often, these schematics are outdated, incomplete, or do not exist at all. Without this map, governments and other organizations can make good choices about how to maintain or extend the grid. In high-income economies, utilities use sophisticated sensing devices to assess and monitor this infrastructure. These methods are labor-intensive and gain complexity when the region of evaluation grows. In developing settings, this task is even harder to perform due to the budget and capacity constraints, which are reflected in the lack of infrastructure, poor electricity reliability, and low electrification rates. In this work, we present a data-driven approach to estimate how the medium voltage power grid is deployed using nighttime satellite imagery, road infrastructure, and land cover data. We aim to build a non-invasive policymaker tool to facilitate the acquisition of power infrastructure data at low cost. Related work, the development seed built a pipeline to efficiently map the high voltage grid at a countrywide scale. The pipeline relied on both machine learning and their data team. The machine learning component processed satellite imagery across an entire target country and returned geospatial locations likely to contain high voltage towers. The data team then overlaid this information on top of satellite imagery and used it as a guide to help quicken the mapping of high voltage towers, lines, and substations. On the other hand, Facebook proposes a system that uses nighttime lights as a proxy to estimate electrified settlements. Using filters, they are able to contain specific points with higher intensities and origin points to run the algorithm. The grid estimation algorithm, which is a modified version of Dijkstra's shortest path, aims to make connections in the most efficient way possible, taking into account roads, water bodies, and ground truth data. Based on our related work findings, our approach develops a deep learning model with the following datasets: imagery from the visible infrared imaging radiometer suite product, road network collected from OpenStreetMap, land cover data from the European Space Agency, and ground truth data from the medium voltage electricity network. Using convolutional networks, our deep learning model takes inspiration from the classic U-Net network, commonly used for semantic segmentation tasks. As input, we have three layers: roads, land cover, and nighttime imagery. The output is a binary mask estimating the probability of each pixel to be part of the electrical grid. We evaluate the performance on our model using two types of loss functions that are commonly used for this type of task: mean square error loss with balancing weights, and dice loss, equation 1 and 2 respectively. In terms of qualitative results, we can observe two patches, A and B, showing the nighttime layer, the three channels together, the predictions with and without thresholding, and the ground truth and predictions with skeletonization. We can observe in these examples that the predictions are biased to roadways, which might affect our estimation. On the other hand, in patches C and D, we observe good predictions when there is some coincidence between roads and power grid. This observation shows that our predictions might depend on the underlying distribution of this infrastructure, which is likely to be different if we consider the context of developing countries versus high-income ones. Also, our outputs show some sort of discontinuity, which might be problematic to measure our performance. F1 score might be a better measure to use if we need to seek a balance between precision and recall, and there is an uneven class distribution, large number of actual negatives in our case, in comparison to the grid pixels. Quantitative results, we try different hyperparameters and test the importance of the land cover layer. We observe that the land cover layer shows significant improvement over the model without it, approximately 20%. Our best result shows F1 score of 55%. For our future work, we plan to incorporate RGB imagery as additional channels, try different architectures, improve the continuity of the prediction using regularization techniques, and try to implement transfer learning techniques from similar tasks. Thank you so much for your attention.